Well, welcome back. This is part two of our introduction to sieve analysis, which is how we characterize certain fine-grained soils. Last time we talked about some very basic concepts, and we talked about how to compute data that from sieve analysis. So in this video, we're going to continue that and show you how to plot the data and then how to interpolate off of that graph some pretty important values to help characterize the soil. So let me share my screen with you and we'll get started. So the most important thing next after we have our data is what's called a particle size distribution curve. So from our mechanical analysis, we plot this data, and because the particle sizes are such a large range from things in the hundreds or thousands of millimeters up to millimeters themselves, we use a special scale on our plot called a log scale. And therefore you look at and you change things to powers of 10. So we're going to use what's called a semi-log scale, which just the particle sizes will be logarithmic and the percent passing or percent finer will be arithmetic. So again, since the particles are plotted on this log scale, then and the finer will be on arithmetic scale. So here's a typical graph. Now you can see the 200 sieve right here in the middle becomes a delineation between sand and silts and clays. Most of our work will stay to the right of that line. And the thing to notice right off the bat is the scale down here at the bottom. It starts off at 1/1000th of a millimeter all the way to 10 millimeters. So you can see that the particle sizes for this range between 100th and 1,000th of a millimeter have the same space as 1 to 10. And if you look carefully, you'll see that the main units on each of those lines is just a power of 10. So we have 10 to the 1, 10 to the 0, 10 to the -1, 10 to the -2, 10 to the -3. So this scale will be on base 10. So this is our recommended procedure of how to do the sieve analysis. We'll weigh each sieve empty to 1/10 of a gram, or the accuracy of our scale. We'll get our soil sample, try to select one that's uniform and representative of the group. We'll weigh that. You want at least 500 grams. You don't have to have exactly 500 grams, but around 500 grams. And then we'll put the material into the sieve and put it into the machine and let it shake. I usually let it shake for about 10 minutes. Then we carefully separate the sieves and we weigh them again. So you have a weight of the sieve empty and then a weight of the sieve with material trapped. The difference is the mass retained on each sieve. And you just go through each sieve carefully, weighing them before and after. And then when you're done, we just usually throw the material away, clean the sieve as best we can, and then we're ready for another example. So we've already talked about the calculations previously. You would do the percent weight or percent retained on each sieve. That's the weight retained over the total. Then we do the cumulative percent retained. We talked about that in a little more detail in the previous part 1 video. You can look back at that. And then we did the percent finer, which was 100% minus the cumulative percent retained. This is a little summary of our calculations. So what we want to end up doing with this information is calculate what's called the effective size, the uniformity coefficient, and the coefficient of gradation. So the effective size really tells you kind of what's the smallest size in your sample. So everything will be about that and bigger. Uniformity coefficient gives you some measure of how uniform the smaller particles are to the bigger particles. And I don't have a nice explanation for coefficient of gradation. We don't usually use that in our project work. We focus on a effective size and the uniformity coefficient. Now the effective size is what's called the D10. Now the D stands for diameter and the 10 stands for 10% passing. So what is the diameter that 10% of our material passes? That means the other 90% is retained. So you can see the D10 is a measure of kind of the low end of our particle sizes, and that would be called the effective size. How do you find D10 on the graph? Well, let's say we have a graph that looks something like this. And where did I get this graph? Well, this would actually be the plot of the data that we computed in the part 1. You would plot particle sizes versus percent passing or percent finer. So once you've done that, you have a graph that looks something like this. And now we want to find the D10. Well, you already have percent finer as part of one of your axes. That's the arithmetic scale. You'll notice the bottom scale, the X scale, the sieve sizes are the log scale. So you just find the 10% passing line on the graph. I don't have grid lines on this graph, so I just drew a line at the 10% passing. And where it intersects our curve, and we go straight down, that will tell us the particle size that is 10% passing. Now, sometimes that's going to be kind of difficult to read. So how do you read a log scale? So let's kind of take a stop here, and let me show you how to read a log scale manually. So in science and engineering, these semi-log graphs or even fully log graphs are a way to visualize data that has a fairly large range and kind of an exponential relationship. So in this case, we're plotting our x-axis on the logarithmic scale. So this is very useful, again, when you have a large range of materials, like we showed before, going from very, very small possible silts and clays up to larger particles that you can actually see. So the advantage is it brings out the features in this data that you wouldn't normally see if you were to plot it on a linear scale. So we usually use base 10. You can use base E also, but we'll stick with base 10. So here's what a log scale looks like. So you see I have two scales or two cycle scale. I'm going from 0.1, which is 10 to the minus 1, to 1, which is 10 to the 0 power, and then to 10, which is 10 to the 1 power. So you can see if I were to divide this up, this is 1 power of 10 here, and then a second power of 10 here between those two. You can see it's quite a bit difference. I've got 0.1 to 10. So just to show you how it works, from 1 to 10, each tick goes up by 1. So you'd have 2, 3, 4, 5, 6. You start to get pushed in pretty tight on the right. 7, 8, 9, 10. So that accounting goes through each scale is the same. You just have to look at the beginning value to know what the increment is. So you can see if you look right in the middle of the scale, it's not 0.5. This would be the kind of the arithmetic middle. And you can see the 5 is way to the right. So there also, the paper, the log paper is actually taking the logarithm of the number for you automatically. So looking at the scale on the right, we'd start at 0.1, and that'd be 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then one more would be 1. So that's the way the log scale runs. So let's look at some numbers. So what would that number be? Well, the first thing I like to do is to find the tick mark to the left and the tick mark to the right. So to the left, you can see that would be 0.2, and then to the right will be 0.3. So kind of connecting back to our significant figures work, we all should say that number is going to be between 0.2 and 0.3. So our first significant figure would be 0.2. Now what we do after that becomes a little bit of a guess. It's kind of right in the middle. That doesn't mean it's 0.5 necessarily. It could be 0.2, 0.3, 0.4. So it gets a little trickier. So when we read these graphs, we'll make an estimate for the second significant figure. So in my case, I said it was 0.24. Now, when you read it, you would get 0.2. Do you get 4? Do you get 3? Do you get 5? Do you get 6? That's up to you. Probably not 6, but we should be somewhere in the bottom half of that group. Now, what about this one? I'll give you a second, see if you can try to count where that one would be. So what would be the first decimal place for this one? Yeah, so I counted up and I got between 0.8 and 0.9. So it's going to be 0.8 something. This one's really shifted to the left. So I guessed my second significant figure to be 0.82. How about this one? All right, take a minute and see if you can figure out what values it's between. So if you count over, you can see it's between 4 and 5. So it's going to be 4 point what? You can see it's really pushed to the right, very close to 5. So I guessed 4.9. Again, the guess is the 9, the 4 is not. So remember, in significant figures, the last value that you see, the last significant figure, is the one that you're unsure about and you're approximating. So with that as a background, let's see if we can go back and find our D10. So remember, we had this graph, and we'd already found where the D10 line was. That's the horizontal line at 10 or 10% passing. And we connected it and we dropped it down, and now we're going to read it. I'm going to blow that up a little bit so we can see it a little closer. So now, remembering what we did before, it's going to be between 0.09 and 0.09 and 0.1. So we all should get 0.09. What you choose is a little up to you. I see the line as being very shifted close to the 0.09, so I said 0.093. And that's D10. And remember, D10 is the effective size for this sample. Now, the second thing we calculate is called the uniformity coefficient. That's the D60 over D10. We just have D10, so we're good to go with that. We just need to find what D60 is. So D60 is going to be the diameter where 60% of the material passes. More than half the material is smaller. And that means 40% of the material would be larger. Let's go back to our graph. Let's find the 60% finer line, and it crosses our graph. We record that data and then drop down and look at the unit. So what do we have there? See if you can count over and tell me what that one is. Looks to me between 0.5 and 0.6, and it's very close, so I said it's 0.51. Again, you could say 0.52, 0.53, 0.54. I would accept all of those right now. But we all should get 0.5 and then the approximate value. So now that I have D60 and D10, I can compute my uniformity coefficient. My coefficient of gradation also involves addition to D10 and D60, D30. So again, that's the diameter where 30% is finer and 70% is larger. So go back to our graph, find the 30% where it crosses our line, and then look down to the scale. What do we see? Well, if you look carefully, it's going to be between 0.2 and 0.3. So I guess 0.25. So now we have all the data that we need. I'll just make a note of it here, what we read before. So we know the effective size is D10, so the effective size would be 0.093. The uniformity coefficient is D60 over D10. You'll notice that the units cancel, so the uniformity coefficient is dimensionless. This is 5.5, so this material is not uniform, as you might expect. Closer to 1, the more uniform it is. And the coefficient of gradation with the addition of the D30 squared, if you look at the values again, millimeters squared, 1 millimeter, 2 millimeter, again, it's a dimensionless number. In this case, it's 1.3. So really, we don't have any context to discuss these values yet. Again, if we were into our third project and looking at filter materials, the effective size and the uniformity coefficient are characteristics that we would use to specify certain kinds of material in a filter. Right now, we're just going to look at it as just a problem. We have a soil sample, and now we've characterized it with typical values. So again, the particle size distribution not only shows you the range of particles, but also their distribution. So you might have a graph that looks something like this. Now, what this graph is showing you is that this is what's called a well-graded material. There's a lot of different materials throughout this. So that's kind of an indication that this soil has particle sizes throughout the range. Now keep that in your mind, and let's look at one that looks like that. And what's the difference here? Well, the bulk of the curve is very vertical. So what it's showing you is that most of the particles exist in this band. So the narrower that is, the more uniform it is. So this is what we refer to as a more uniformly graded material. All right, let's look at a graph that looks like this. Well, what you see here is a band where things are pretty uniform, then nothing's happening, and another band. So there's a hole in the middle here where there's really no particles at all. So that is called, this is a very unique situation. This is called a gap graded material. Okay, so that should bring us to the end of this part. The next part that's coming up, let me stop sharing my screen. The next part that's coming up, part 3, would be to put all this together, and I'll go through an example problem. We'll have some raw data. We'll compute the percent retained, the cumulative percent retained, the percent finer. We'll graph it, and then off the graph, we'll read the D10, D30, D60, and then compute effective size, uniformity coefficient, and coefficient of gradation. Okay, so let me know if you have any questions. Until next time, be safe. Take care.